This lecture is on heap sort, and zero-time complexity analysis. Here's a roadmap of what we will cover. In this lecture, we will start by discussing the application scenario of heaps, or say where heaps can be useful. After that, we will cover the basics of the heaps. All heaps are binary trees, so heaps share many of the important properties of binary trees. Let's get started. Where can heaps be useful as a data structure, or say as a tool? You might have played one, two, or many games. Many of such games have millions of players, and also have leaderboard, like this one that you see on the screen. How do you track the top K players? Remember, there are millions of them, and their scores may change. There might be new players all the time, and those who decided to delete their accounts. In such a scenario where there are a lot of dynamic changes happening to the elements that need to be sorted, the sorting algorithms that we have covered may not be the best options, such as the merge sort or the quick sort. And a scenario like this is where a heap shines. In summary, when you need to perform sorting with incomplete data, or when there are constantly newly added elements, or old elements being deleted, yet you still need to perform sorting task, you should think about heaps. That's a quick overview of where heaps can be useful. Let's move to cover this data structure. As we get to the details, you will understand better why heaps are a good choice for sorting in a dynamic changing scenario. First thing first, let's cover the basics of binary tree in case your memory blurs or you have never learned it elsewhere. So for binary tree, we need to make sure that we are on the same page in terms of these concepts, including node, root, and leaf. What's a node? A node is a fundamental unit of a binary tree. It contains data, or say a value, and references, or say links, to its left and the right child if there are any. All the circles with values that you see on the screen are representations of nodes. So what's a root? The root is the topmost node of a tree structure. It is the starting point for accessing any other node in the tree. A tree can only have one root. In our example, the node with the value of 10 is the root node. So what's a leaf? A leaf node is a node that has no children. In other words, both left and right of that particular node should be null. A leaf node is an endpoint of a branch in the tree. In our example, all the highlighted nodes are leaf nodes. As you can see, they have no children. Based on the three concepts, let's define binary tree. A binary tree is a tree data structure in which each node has at most two children, usually referred to as the left child and the right child. Particularly, there is a special type of binary tree that's highly relevant to our discussion of heaps, because all heaps are complete binary trees. So what makes a binary tree a complete one? In a complete binary tree, all levels are completely filled except for the last level, which is filled from left to right. For example, this is a complete binary tree because all levels are completely filled. For another example, this is also a complete binary tree. As you can see, the last level is not fully filled, but it is filled from left to right, so it is a complete binary tree. Similarly, this is also a complete binary tree. Although its last level is barely filled with any nodes, just one node with a value of 3, which is on the very left side. However, the last level is indeed filled from left to right, so it is a complete binary tree. However, a tree like this is not a complete binary tree. It is still a binary tree, but not a complete one. It has 3 levels, but its second level is not fully filled. Now you know what's a complete binary tree, and you have everything you need to move on to learn about the definition of heaps. So what's a heap? First, a heap is a complete binary tree. Second, there are two types of heaps, max heap and a min heap. In a max heap, the value of a parent node is always bigger than its children. In a min heap, the value of a parent node is always smaller than its children. In this lecture, we will focus on max heaps. As long as you understand everything about the max heap, you will have an equally strong grasp of the min heap. Both max and min heaps have the same basic operations, same time complexity, and serve similar purposes. So let's use an example of max heap to understand it better. An example of max heap may look like this. The root node has a value of 10, and every parent node is bigger than its two children in this heap. There are 3 levels in this max heap, and we count that downward, starting from the root node. This is merely a visualization of a max heap. A max heap is typically not stored in a tree structure like this. Instead, it is stored in a linear data structure like an array. How does that work? Let's prepare an array. The size of this array is equal to the number of nodes as you see in this tree on the left side. How do we use an array to hold all the values of a heap? We will place the values of a heap level by level, and from left to right. 10 is the value of the root node, so we place it at index 0. That's everything you have at level 1. At level 2, you have 2 values, 7 and 5, so we place them at index 1 and 2 in this array, like this. Then, you can move to level 3. The remaining 3 values go to index 3, 4, and 5, like this. Using an array to store a heap's value is convenient, but also puts an extra requirement on us. In a binary tree structure like this, given an arbitrary node, it's easy to tell which node is its parent and which node is its child. However, it's not so easy to do in an array. That said, you need to figure out the relationships between indexes of a node, its parent, and its children. We can deduce and generalize a relationship with a few examples. If you focus your attention on the node sitting at index 1, that's a node with a value of 7. Its parent is a node of value of 10 that sits at the index of 0. It has 2 children. The left child is 3 at index 3, and the right child is 6 at index 4. So we can map these values here, like this. What's the relationship between these indexes? It definitely involves subtracting 1 when it goes from a node to its parent. It may involve multiplying by 2 when it goes from a node to its child. Let's look at another example. The node at index 2 has a value of 5. Its parent is a node with a value of 10 at index 0. It only has a left child 4 whose index is 5. It doesn't have a right child, but if it does, the index of its right child will be 6. So we will add the indexes here. From this example, we can modify our guesses. In addition to subtraction by 1, it may actually involve a division by 2 to derive the parent node's index. 2 minus 1 will get you 1, but 1 divided by 2 will get you 0 if you limit your calculation to only integers. To get the index of the left child, you can do 2 multiplied by 2, then plus 1. To get the index of the right child, you can do 2 multiplied by 2, then plus 2. Let's look at another example to verify our guesses. If the given node is 3 at index 3, its parent node's index will be 1. It doesn't have any children. Let's assume that the heap will grow to the extent so that it now has 2 children. That will be here and here, and their indexes will be 7 and 8, like this. Given the node at index 3, if we subtract it from 3, then divide by 2, we will get 1, which is the same as the index of its parent node. If we multiply 3 by 2, then plus 1, we will get 7, which is the same as the index of its left child. If we multiply 3 by 2, then plus 2, we will get 8, which is the same as the index of its right child. That said, our guesses on how to derive the indexes of the parent and two children is largely correct. You can move on to prove this via induction if you want. You can also verify this by referring to an external resource or a generative AI tool. We will skip the proof part here and jump to its generalization directly. When we use an array to store the data of a heap, given an arbitrary node at index I, the index of its parent node is I minus 1, then divided by 2. The index of its left child and the right child are 2 multiplied by I plus 1 and 2 multiplied by I plus 2, assuming that it has two children, of course. This knowledge is important because it allows you to navigate around and go from one node to its parent, or left or right child using indexes. This knowledge will support us when we cover the basic operations of a heap. Beyond the mapping from a tree-like structure of a heap to an array, there are 3 features of a heap that you may want to know. They are very important when it comes to analyzing the time complexity of the heap operations. First, the relationship between the number of nodes and the height of a heap. Given a heap, if we assume that its leaf level is fully filled, the height of the heap, h, and the number of nodes n can be expressed as h is equal to log n. You might have already seen this in the past, and this is something that you can prove via induction. We won't be doing it here, but we can show you a few examples that will lead to the induction. When the number of the nodes is 3, the heap height is 2. Log 3 is about 1.6, which is almost 2. When the number of the nodes is 7, the heap height is 3. Log 7 is 2.8, which is almost 3. When the number of nodes is 15, the heap height is 4. Log 15 is 3.9, which is almost 4. You get the idea. Second, given a heap, if we assume that its leaf level is fully filled up, the relationship between the number of nodes at the leaf level is in proportion to the number of the total nodes at a fixed rate. In short, if there are n nodes in total in a heap, the number of nodes at the leaf level can be estimated as n divided by 2. You can prove this via induction if you want. More than that, you can further generalize this pattern to the number of nodes in other levels. If you go from the leaf level to the root gradually, level by level, the leaf level contains roughly n divided by 2 number of nodes. The second bottom level contains roughly n divided by 4 number of nodes. The third bottom level contains roughly n divided by 8 number of nodes. When you go up one level, you can estimate its corresponding node numbers at that level by further dividing n by 2. Intuitively, this pattern tells you that the majority of the nodes are near the leaf level in a heap. The leaf level contains 50% of all the nodes. The 2 bottom levels contain nearly 75% of all the nodes. In this video, we discussed where heaps can be applied, we covered binary tree, and introduced you to the concept of heaps, including how to store the data of a heap in an array, as well as some basic patterns of a heap. In the next video, we will cover the basic operations of heaps, including the insert and the pick method.